Okay, let me see really quick. Changing my output settings really quickly. Okay, well, my headphones are not working today, so I'm just going to speak out loudly onto my laptop, and we're going to get started. So it looks like that a lot of you have gone forward and started on the HOLA, which is great. Let me switch this view really quick. Share screen. Okay, and I know I've mentioned this, every week. I'm going to keep mentioning it. We're getting closer now, so please remember, if you haven't completed the discussion, then go ahead and go into there probably by the end of the week. I'm going to just keep reminding y'all. And it looks like that we had some of our classmates go ahead and submit your discussions. So please go onto here, onto Canvas, and submit your discussion here. It's 5 points of your grade. Additionally, I don't intend that everyone has their poster submitted right now, but if you are almost complete or completed, you can go ahead and submit it. Of course, the due date is May 1st, but once again, I will always remind you to work on the project earlier than later, just because finals are going to be coming up, the exam's going to be coming up, and I want to make sure that everyone has that kind of out of the way before the exam comes. So let me go ahead and open up the syllabus for half a second, so that way we can see where we stand. So the classes are coming to the end now, and I wanted to just share with everyone where we stand on the syllabus so that we're all on the same page. So we are Group C, and we did SN1, SN2 reaction on the week of March 22nd. Last week, gas chromatography. This week, we're going to be doing the bromination of Stilbene. And then next week, we have dehydration of cyclohexanol. And then, so reminder, the exam is online during the class period. And you need to make sure to have either a Texas state ID, your driver's license or passport, some sort of identification that has your first and last name on it. And during the exam, your cell phone can only be used as a scanner. The online exam will be through Zoom and IA proctoring, so I'll be here to proctor that. And the exam will be as per our lab day and the section time, and the exam will be recorded as a formality, so that way that we make sure that everyone is being academically honest during the exam. If you need to review exactly what entails performing the exam, please make sure to review this area here on how you need to have your phone set up to show the recording of you performing the exam. I would recommend to have it kind of like plugged in, maybe set up against something. Just make sure that it's to where we can see part of you and part of the computer, to make sure that everyone's being academically honest. The grading scale, of course. And let's see, I saw another portion here I wanted to see. Okay, so the exam policy. The exam will be during our class period, and we need to make sure, once again here, the photo ID. Please contact me ahead of time if there's some situation regarding your photo ID, and we could probably work something out so that way that everyone, has their verification of their person. And the exam, I would say, will be formatted the same way that all of the data analysis questions are. So I would review all of the lab notebooks that you've done, and you can probably review the quizzes as well. And that way that you will, I would say that in my experience from all of the lab exams that I've taken all throughout my undergrad, they were all open-ended questions, some of them reactions that we've performed, some of them asking you about fundamentals, just understanding everything that we've gone throughout the semester. So maybe we can do a brief review next week at the end of our lab period if people would like that, so that way we can briefly touch onto all of the subject material that we've covered in the class. And from what I know currently is that there's not some sort of exam review, like pre-test or You know, sometimes people, they give some sort of test exam or some sort of review before the exam. So I may try to format some sort of small run through so that way everyone can get fresh on their mind what we're going to be covering during the exam. And I'll discuss with Dr. Ostogi more next week because I meet with him on Monday nights so that I can tell everyone Tuesday morning exactly how we're going to perform it. And then if people have the time to stick around on Tuesday, then maybe we can go ahead and review it. Yes, so it will, the final exam will be proctored by me in the sense that, you know, you'll just have your camera there and I'll be making sure that everyone's being academically honest behind their camera. That's basically it. And I believe that everything would be performed like through Examity, and they would, you know, anything that you need to scan would be written on paper. And then once everything's scanned up into the system, then I will go through and grade everyone's, you know, extra stuff that needs to be reviewed on paper. So yeah, so this is basically just a quick overview. My biggest recommendation for studying for these kind of exams is they like to go through and go to the highlights of certain sections. So what is the main concept that you learned in each section? You know, for instance, what was the difference between SN1 and SN2? That would just be like a brief situation that we would cover in that system. They would cover something along the lines of, you know, how would one perform recrystallization and what is the purpose of performing recrystallization? Maybe the differences between reverse phase and normal phase column chromatography. You know, I'll go through a very in-depth analysis of everything and the key points that I believe would be asked on the exam. It's very cut and dry. Whenever I've taken the exams, I've always overstudied, and then when you look at it, then you say, oh yeah, of course, like this makes sense. Like here's a question, and they say, is this SN1 or SN2? And then immediately you would be like, oh, okay, well I reviewed it. You know, tertiary halide, that's obviously SN1. Just as a brief question that I just made up off the top of my head. So yeah, so if they say on there to not use Chromebook, then I would advise not to use a Chromebook. That is at your own risk. We do have, you know, computers on campus that you may use. And if there is an issue with regards to the Chromebook situation, I would discuss it with Dr. Ostogi. I'm not the one that creates the syllabus, so I don't really have a personal anecdote as to why a Chromebook would not be allowed. But I would assume it'd be something with regards to access, or sometimes people have issues with things loading on their computers, and that could possibly be through maybe like a Chromebook or iPad issue that they're mentioning there, and they've had that kind of issue before. So if you have specific questions that you see within the syllabus regarding the exam, you can feel free to contact me. But if I don't have a direct answer, I'm going to forward you to Dr. Ostogi, because, you know, I don't really know the niche situations regarding platforms and software that would be necessary for the exam. So regardless, I will definitely get some updates for the exam. I would just recommend, you know, when you have some time, some spare time, review the lab manuals that you have, review your lab notebooks, and I will try and see if the documents are not open currently. I was hearing that grades were closed. Then I will try and see if Dr. Ostogi can open them up for everyone to be able to review the edits to their lab notebooks that need to be corrected. Because the thing is that if you got a data analysis or post-lab question incorrect, that may hinder your performance on the exam. Because if you don't understand a certain concept, or that you answered a post-lab question incorrectly, and then you go forward and repeat that on the exam, then, you know, unfortunately, that would be a replication of misunderstanding and that you possibly learned something incorrectly. Because a lot of concepts, they are black and white. Like, they are just it is either SN1 or SN2. And I just have that in my mind right now as an example. But in chemistry, when you learn something, if you learn it a certain way and you say, oh, this is the way that it is, if you learn it incorrectly, then it could actually be the other way. And I want to make sure that everyone has their specific answers correct, so that way that you can study the correct material for the exam. So going forward today, we are going to be covering bromination of Stilbene. So let me go ahead and share my screen here for the module. Okay, so like usual, we're going to be covering the lab manual, and the lab manual is extremely short for this one, so I would like to review the video with everyone here. So I will play that after we walk through the lab manual, as it is maybe a 10-minute conversation over the lab manual. Additionally, I would recommend to watch the other videos. They're very helpful, especially like the video 2, testing for haloalkanes. This is like the silver nitrate test that I sent y'all last week, and it's essentially the same thing, the precipitation, the same similar concept with regards to that and how bromine performs a precipitation in a silver nitrate solution. So we can watch that also briefly. And then the third and fourth video I would recommend to watch additionally, just to absorb more of the material. And so then make sure that your quiz is completed. And then let's see. Of course, the post-lab notebook, make sure to complete that. And then the data we can review here afterwards. So let me switch back, come over here. And let's focus here on to lab manual. Okay, so within chemistry, there are multiple sorts of reactions, and the most common ones are nucleophilic addition, electrophilic addition. In this instance, the one that we will be focusing on this week will be electrophilic addition. So the electrophile, we know that the electrophile, they want electrons. The nucleophile is a nucleus seeking, it's seeking the center, and it wants to obtain an extra electron. You can note it as something on the end of the periodic table, such as a halogen that is very close to fulfilling that 8 electron rule. However, it's missing one. So in this instance here, what we'll be reviewing is this compound known as Stilbene, and I'll show you the image going further down. But on a basic level, let's firstly understand exactly what electrophilic addition is. So firstly, in an alkene is a carbon-carbon that is double bonded together. So you can see it here. It looks like an equal sign or 2 lines that are on top of each other. And the one thing that is good about alkenes is that they act as nucleophiles themselves. So an alkene can actually undergo an electrophilic addition by the pi electrons. So the electrons that are around it, not the sigma bond, but the pi bond, those pi electrons can attack an electrophile, just like a nucleophile can attack in an SN2 fashion. A nucleophile can come in and attack and then immediately make the leaving group leave. In this instance, the alkene is acting as the electrophile, or sorry, the alkene is acting as the nucleophile, and the electrophile is the one that's donating its electrons or being attacked by the alkene. So firstly, through the pi bond, so it's not from carbon 1 or carbon 2, it is from the pi electron itself, the cloud that is around the alkene that is attacking the electrophile. So firstly, it attacks the electrophile, and then the electrophile binds to one of the host sites, whether that be carbon 1 or carbon 2. That's more of an advanced organic chemistry situation where you would want to know exactly where the electrophile would bind to firstly. But in the instance that we're talking about here, we're going to think about it in a common situation where it would just be equal on both sides. Let's just say there are carbons on each side. So it doesn't matter where it goes, left or right. It just binds to one of the carbons. So now the electrophile on this instance is bound to the left carbon. So therefore, the right carbon is going to become a carbocation. And this is because the electrons have already been donated over to the electrophile. However, the alpha carbon is now depleted of electrons. So what happens in that instance is that the nucleophile can come in and donate to the carbocation and attack that carbocation. So what you're left with is now you have a carbon, an sp3 carbon. It was an sp2 when it was an alkene, so now it's an sp3. And the sp3 is now bound on one end to this electrophile that was created by the alkene attacking the electrophile. And then with a carbocation intermediate, then a nucleophile comes in and can also attack on the alpha carbon. So in this instance, we have disubstituted alkanes. We turn our alkene into a disubstituted alkane. Both carbons are attacked, and they are left with, the electrophile on the left side and the nucleophile left on the right side. So in this instance, the most common halogenation reactions are known as chlorinations and brominations. So for this instance down here, which I'll explain further, we would be performing a dichlorination reaction, sort of electrophilic addition mechanism, following the same pattern that we have of the alkene attacking electrophile, leaving a carbocation at the alpha carbon, and a nucleophile coming in and donating to, fulfill the nucleophile's role of meeting that 8 electron nice orbital where everything is neutral, we're happy, and we're fulfilled. So the good thing that is actually used in industrial situations is the production of ethylene dichloride. I've also mentioned it earlier in our class periods. You've heard it as DCM or dichloromethane. In this instance, it's dichloroethane, but mostly in the lab, a lot of DCM is used instead, which is methane instead of ethane, just a singular carbon. Secondly, in industrial situations, they make PVC. Everyone knows of, as plumbing and other sorts of plastic pipes, polyvinyl chloride. And I believe it may be OChem 2 or in maybe the Gen Chem lab that y'all actually perform the production of PVC. It is a vanillic reaction. However, I'm not going to stray off into the gray area there. I'm going to stick on topic here. So when we also talk about these sort of productions and these mechanisms, we want to think about also the stereochemistry. So as y'all have been learning or have learned, is the either trans or cis conformers that are produced. And as we know, like trans is a cross. And so there'd be one up and one down. And cis is the same on both sides, either up, up, or down, down. And so in this situation, we want to understand exactly what's going on. And we would understand that in this mechanism of an alkene halogenation, we would be forming a trans product. And the reason that we're forming a trans product is understood because of the chlorinium intermediate. So here, this may look a little confusing because in the first instance, we're left with a carbocation on the alpha carbon. But in this instance, what happens is that the alkene firstly attacks the chloride, right? Then we have a good leaving group, a chloride. One of the chlorides now leaves. So what happens is that since the alkene has attacked from the pi bond itself, it has actually created a double bonded intermediate. So there are actually 2 bonds individually from each carbon bound to the chlorine. And you can also see that the chlorine is not a neutral charge in this instance. The chlorine actually has a positive charge. And this can also be denoted as something in terms of like a carbene, where there's a positive and negative charge simultaneously on a compound. And so in this instance, the chlorine is actually positively charged. It has 2 bonds onto it, and it is currently not fulfilled. So what happens is that since we have this chloronium intermediate with 2 bonds, one from each carbon, an extra chlorine, the one that was actually left from the original, the step 1 in the reaction, in step 2, the chlorine comes back in, acting as the nucleophile, attacking the alpha carbon and displacing the electrons that are double bound to this chlorinium intermediate, and makes that chlorine neutral. And then obviously the chlorine acting as the nucleophile here, as you can see, comes in and displaces that and allows there to be a totally neutral system. Now you've had a dihalide reaction occur. And as you can see, the chlorine, as we know from SN2 reactions, does a backside attack. So one chlorine is now on the top, and then the other chlorine intermediate has now broken and come down to the bottom. So you'll have one chlorine here and one chlorine here, one on top, one on bottom, and you've created a trans substituted product. So just remember that we create a chlorinium intermediate in the instance of using halides. The same situation happens with bromines and commonly can happen across bromination reactions going forward. So as I say here, the incoming nucleophilic chloride ion is forced to attack the top side of the cyclohexane ring because the bottom side is shielded from attack by the positively charged chlorinium species. So similarly, if you want to think about it in a sort of magnetism situation, we know that if you try to put 2 positive charges together, then it will actually repel each other. And so in this instance, the positively charged side there is acting like a shield and not allowing the other chlorine to come in under the bottom. So they would also call this an anti-addition, creating the trans product. And so similarly, we would have the same situation as within using bromine. We create a brominium ion. Unfortunately, they did not show it here as a sort of intermediate. But if you were to think about it here on this stilbene, then you would have a brominium intermediate as an intermediate step, and then the other bromine would backside attack from the bottom in the instance if you're thinking about it being substituted on top, or vice versa. If you want to think about the bromine substituting on bottom with the brominium intermediate, then the other bromine will come back in and attack from the top. So whichever way that you draw this within your own mind, just remember that there is an intermediate where there are two bonds, an alpha and beta carbon bound to a brominium or chlorinium intermediate. And then there follows with a subsequential backside attack by one of the halogens, whether it be bromine or chlorine, depending on what you're using in this sort of reaction. So going forward, one part here that's kind of talking about a safety method within regards to performing these 1,2 dihalogenated reactions, we want to understand is that within lab, there are certain things that are dangerous. One of them being bromine. Bromine is simultaneously a liquid and gas. If you use it in lab, what it does is when you open up the vial, it will start fuming, and that will start creating bromine gas. So simultaneously, it is a liquid, but it is it's very volatile. So the thing is that commonly they would not want undergrads in this situation utilizing liquid bromine. If you don't have common use of liquid bromine, it is very dangerous. I've spilled it before. It was a whole situation. I freaked out and I was like, oh my gosh, I can't believe I spilled it. Fortunately, I was okay. I was wearing 3 pairs of gloves and fortunately no damage was done. However, I did quickly learn from that bromine is very dangerous and had to go forward to, advance my chemistry techniques so that way I could use it. However, in this situation, we will actually be using the organic salt pyridinium tribromide, which is much more safer. Obviously, you'd still be needing to use gloves so that way that it doesn't irritate your skin or sort of cause any sort of damage to your own person. So we would want to be utilizing the organic salt pyridinium tribromide. And here, well, what exactly is pyridinium tribromide? That is not 2 bromines bound together, that's 3, right? That seems a little confusing. I don't understand how that you can do a disubstituted reaction when you have 3 bromines. So the good thing is that down here, they've shown you a schema of pyridinium tribromide and the molecular bromine equilibrium. So what happens is that bromine can actually dissociate from this tribromide bonded anion here. So what it does is it creates the pyridinium monobromide, and you create your dibromide, or just bromide is actually what it's called when it is in the dibromine form. So utilizing this within a solvent system, you put in your pyridinium tribromide and it will dissociate within the glacial acetic acid in order to create your bromide. And then going forward, the bromide can go and do its first electrophilic addition, followed by the subsequential nucleophilic addition onto our stilbene. And additionally, because I did briefly just jump over it because we were kind of getting into the midst of this electrophilic addition, I need to mention that this is stilbene. Stilbene is 2 benzene rings bonded by an alkene in the center. You can also look up other sort of compounds. One compound that we create in our lab is azobenzene. However, it is a stilbene in the sense that it has a nitrogen right here on this side and on that side, and it is double bonded in the center. But for this instance, just remember that stilbene is 2 benzene rings bound together in the center by 2 carbons here that are actually an alkene. So what happens is that we can take our bromine or chlorine in the other example given, and then we can disubstitute it here in the center. And going forward, in this experiment, we would be given an unknown stilbene, whether that be trans stilbene or cis stilbene, and then that would go forward to make 2 different sort of products in that situation. And this would also have to do additionally with steric hindrance with regards to how this would add. And so going forward, you would still you would still have your trans addition to the Stilbene regardless because of this reaction. However, what would happen is that you would end up either with the trans Stilbene like this, and then you have your dibromines, or you could have the cis Stilbene, which would be both benzene rings down or both benzene rings up, and then the bromines attached. The bromines would still be attached in the anti-fashion, where they would both be trans. However, the benzene rings would both be up or down. So regardless, the addition is as it is. It is just that there are two different conformers, the cis and trans Stilbene, and that is important to know because what happens is when we synthesize brominated Stilbene in this lab, they have significantly different melting points. So you may think, oh my gosh, I'm not sure, how would I know, like, just going forward? Well, what happens is the Stilbene, if we brominate it, it's going to be near 238, give or take, probably more because the bromines are on there now. Same thing with the cis Stilbene. We're adding bromines. It's going to become, higher melting point. However, it is such a large difference. It's over 100 degrees Celsius difference. So we would definitely be able to isolate and understand exactly the quantity or the form of compound that we created afterwards if you were given an unknown solution, because you could take it over and run the melting point machine and it would be extremely distinct at whether you got, let's just say 130 melting point or 250. And I'm just throwing numbers out there because I don't know off the top of my head exactly how much it is, but it is over 100 degrees Celsius difference. So that is a very distinct amount. So going forward, it should be noted that vicinal dihalides react with alcoholic silver nitrate to form a precipitate of the corresponding silver halide, just as in the reactions that we performed last time. And finally, we only have a few questions here, so please make sure to do your due diligence with regards to completing this, since we only have these two here. And it is a very basic setup here. You take a round bottom flask, you put a boiling stones in there, then you weigh out your Stilbene, add it into your round bottom, carefully add in your acetic acid, your pyridinium tribromide. Then what you do is you go forward, you assemble your reflux apparatus, you set in your round bottom flask into a sand bath, then you attach your water lines onto your condenser, making sure that they're very secure so that way that they don't pop off and shoot water all over the lab. Then the water goes in and it cools down the solution so that way that we create this refluxing situation as we reviewed in our earlier classes. Then we bring it to a boil, the reflux starts, and we reflux it at the given boiling point of acetic acid for 15 minutes. You'll see the color change within the reaction. You remove the apparatus from the sand bath, cools down to room temp. Then the workup is super easy. You just add in DI water, 25 milliliters in this instance. Then you put the vial into an ice bath and the compound nicely precipitates out of your reaction flask. Then you go forward and you perform the filtration on a vacuum apparatus like we've used before. So then afterwards we dry it under vacuum, and then once it's completely dried and all of the water is gone, we can go forward and weigh out our product. So it's a very straightforward reaction, and I will briefly jump through and show everyone here the video so that way that I can give everyone a quick view of that. So one moment here. Okay, they set up all of the stuff that we've discovered from our lab manual. Then we go forward and get our glassware. We have our round bottom flask and our beaker. Then we have our vacuum flask, our Buchner funnel, graduated cylinder, condenser, spatula, keg clip, if I'm not mistaken, a bulb. And the keg clips, they're not entirely necessary, but they are helpful for kind of just holding things together within lab. Most of the time when you set things up and you've greased the apparatus correctly, then everything will stay locked in place. So we have our Stilbene, We have our red pyridinium tribromide, and on the side we have our ethanol, acetic acid, and in commonplace situations, we would be setting up these reactions within the hood and not out on a bench. Silver nitrate in order to perform our precipitation. And, oh yeah, let me go ahead and make this theater mode so it's a little bit more visual for you all. So we weigh it out. I'm going to skip over this because everyone knows how to weigh stuff at this point. Go forward, record all of your masses. Then we take our glacial acetic acid, we add it into our round bottom flask with our boiling stone. Go forward, add our pyridinium tribromide and our stilbene into our reaction flask. Okay, so then of course, always remember to grease any sort of glassware that you put together that is heated, just because glass expands and contracts, you know, heating and cooling. Everyone knows about, you know, glassware can shatter if it's hot going into a cold system very quickly. So that's an additional safety measure you might want to mention. So yeah, they put the keg clip on there just for the sake of holding it together a little bit better. But of course, in a safety situation, you would not want to be holding it over, you know, just holding it in open air for too long. So we swiftly set up the sand bath, or in this case, an electric flask. So we have our condenser hooked up here, and you know, we always put in the water going in from the bottom and out through the top, exhausting down into our sink, so the water is pulling the heat out and going down. Then we start up our heating. So now we have it actually boiling, and it took 12 minutes to set up. It's kind of an arbitrary number. It just depends on how long it takes for it to heat up. The boiling point's at 118 degrees Celsius. So now that it's over here and boiling, we let it reflux for 15 minutes. Okay, now once it is done here, then we have our beaker over here with some cold water in it. We pour our solution over, and you can see we have a little bit left in our round bottom. So what we can actually do is add in a little bit more DI water in order to pull the rest of our product over and pour it into our beaker. And then the solution will cool and the precipitate will come out. It is only slightly soluble in acetic acid, mainly whenever it's boiling. So commonly in lab, we'll utilize a solvent that will only have our compounds soluble at the boiling point, or, you know, it's kind of like recrystallization in that sense. And what happens is when we cool it to room temperature, we have a nice precipitate. So that way we can just go forward, either cool it over ice if we need to force it to precipitate out. And then we can run it over our vacuum filtration and pull it on our Buchner funnel here. So she's just wetting it here to prepare it. And then we take our compound here, it's all precipitated out, pour it over, vacuum filtrate it, and you can see that the clear liquid is coming through, so that's a good sign. Whenever you perform vacuum filtration, if you see clear liquid, that means it's good because you are leaving all of your product up at the top. Sometimes product can kind of slide out through the bottom of the funnel, and you would have to perform a secondary filtration. But, you know, we always try and prevent that just to save time and resources. So yeah, of course, y'all know, you know, you just keep pouring and pouring and pouring. And they're going to perform a rinse with water to pull the rest of it out of this flask. Then let me see really quick. Then they let it dry in the oven, go forward and weigh it out. And let me see if they perform the silver nitrate test on this video. I don't remember. So the thing with the silver nitrate test that is important is to understand the differences, because all of these are white solids, they create transparent solutions. However, when you add in silver nitrate, the key thing here to understand is that with the chloride, you'll create a white solution. With the bromide, you would create a cream solution. And with the iodide, you would create a pale yellow solution. So these are indicators for us to perform the halide ion test. So in this situation, at the bottom, it says here that you would want to take in your dibrominated stilbene solution and add it with your 1% ethanolic silver nitrate and allow it to mix for 5 minutes, let it kind of stir up. And then in the situation, since we have bromine, we would create some sort of cream solution. So let's see, did they do it? No, they didn't. Let me open up the other video so we can briefly watch that, and then we can go forward with our day. turn this off. So this is explaining the nucleophilic addition using sodium nitrate, nitric acid. Let me jump over here. Yes, so in this instance, you have your bromine and you're adding in your silver nitrate. And sorry if the quality is a little low, you may have to rewatch this video later. But what happens is when we add in the silver nitrate, you see a cream solution and creates, well, in this instance, this would be silver chloride. And so in this example here is the silver bromide precipitating out. And that's what you would create after about 5 minutes of having your compounds stirring or just mixed up in there. It just takes a little bit of time sometimes. And yeah, so this is what you would actually create at the end of the day. So when you see the cream solution, that's just the silver bromide kind of dispersed throughout the whole entire solution. And then as you see here, over time, eventually that silver precipitates down to the bottom, and then it creates this, and the water is not as clear anymore, but it is definitely very apparent whenever you create this sort of system. So that would be about everything I would like to cover today regarding this. And if you have any further questions, please let me know now. With regards to the post-lab questions, yeah, there's just those. It's a very short section this week. And if anyone else does not have any further questions, you're free to go. If you have questions, feel free to stick around.